This section will take a more detailed look at polar graphing. So here are some notes to go through a little bit to give you some ideas of shortcuts. We can always just plot points. If you're not sure how to graph something, plug in a bunch of values for theta, get values for our plot your points and see how they connect up. But there's some general classifications of certain types of graphs. First of all, there's the limicons. You've got the limicon over here, the limicon here, which is the specific one, the cardioid, because it looks like a heart. And there's also this one with the inner loop. Then we have roses, where if n is equal to odd is an odd number, then we have n leaves, because really there's two n, but they double over each other. If n is even, you have two n leaves because they don't go over each other, so you see all of them. Here we have some circles. R is equal to a constant is centered at the origin. R equals a sine theta or a cosine theta gives you these particular circles. Lemniscates is r squared is equal to a number sine 2 theta. Is this lemniscate over here? It's sort of two loops. R squared equals number cosine 2 theta gives you these two loops. Spiral is simply r is equal to a constant times theta, because as theta is changing, r is changing right along with it, so it's either spiraling in or out. This isn't necessarily a process I would use, but it gives you some good ideas of ways to think about it. Think about what type of curve you have. Figure out maybe what sort of symmetry you might have. Look for specific points. Reference angles, also 90, 180, 270, 360 are good ideas. Find out maybe the maximum length you're going to be going out, keeping in mind that cosine of 0, cosine 360 gives you 1 and sine of 90 gives you 1, which is often useful to see how far out you're going to go from the pole. And you start to graph and label and put everything together. Now, as far as using the calculator to do this, if we start off with, say, theta divided by pi over 4, which is a spiral, and we're going to go from 0 to 20 pi with theta step of 0.1, our y min, y max is negative 5 to 5, our x min, x max is also negative 5 to 5. So 0 to 20 pi is going to be 10 revolutions of this spiral, and so maybe we're not going to look at all of them, but one thing I want to point out here is the theta step we used was 0.1. And so what happens with 0.1 is that every 0.1 that theta increases, the calculator lays down another point. So you get a pretty smooth version of the curve. It takes a little while to come through, but it's pretty smooth. So here comes our spiral. We get 10 revolutions. It's taking a little while, so I'm going to press on to stop it. It's going to take a moment to do that. You can see in the upper right corner there it's stopped now. If I go back to the window, instead of making it 0.1, I make it 0.01, I'm going to get a much, actually 0.01 up here, I'm going to get a smoother spiral, but it's just going to take forever for it to work. And so now if I graph it, we wait, and we're not going to see too much because this is 10 times slower than what we just did. And so it's a trade-off between getting a good accurate graph and doing something in a timely fashion. So we're still waiting. We're just finally now seeing some little point show up. There's another one because they're so close together. And so that's just not worth our time at all. So we'll stop that one. And now seeing what happens when we go the other direction with theta step is instead of doing 0.1, if we step it up to say 1. So now we're going to get every single radian we get at point. Now 1 radian, I mean now we're getting towards 60 degrees, so this is going to be pretty sloppy. And you can see we just lay down these points, and okay, it still looks vaguely spiral-like, but it puts straight lines between all the points. This time we'll let it go all the way around, so there's our 20th revolution. So clearly 1 is too big, and then it gets obviously really absurd if you start using a theta step of something like 5. I mean, it looks like a completely different curve, basically. So now it looks like it's going the opposite direction. It's sort of like the idea when you look at helicopter blades. They seem like they're going the opposite direction slowly sometimes, depending upon how fast your eyes can pick up what's happening. Well, it's the same idea here, that it's only laying down points every 5 radians, and so because of that, it seems to be going in the opposite direction. So going over to some Geometry Sketchpad files, here we have a plus b sine c theta. So really it's 1 plus 3 sine 2 theta, and we can go ahead and slide along our theta. So as we slide theta, we get different values of r, and we're plotting out the points. So as theta changes, here's r coming through. Now it goes back through the pole. Here's another graph. This is a spiral 3 cosine 0.25 theta. So we see a couple different graphs here. Now another way to think about how we get these is by going to what we know about the Cartesian version and going to the polar version. So here's y is equal to cosine theta. And we can animate this along, and so as theta changes, y goes up and down. Now if we imagine that it's, instead of y is equal to cosine theta, it's r is equal to cosine theta, then let's see the corresponding polar graph. So the angle's changing in the same way. It moves left, right here, it moves counterclockwise. And basically, as I plot along here, whatever y value I'm at here, that's my r value here, and so I get this circle. This is 2 divided by cosine theta, so we'll leave the Cartesian back up there. So we'll animate this point, and here's the corresponding polar. So you can see that as we come back down here, we're at the x-axis, then we go up to infinity, which means I'm going up vertically down to negative infinity, so I'm way down at the bottom. So that's one way to connect the Cartesian to the polar. Another thing to think about, this is a little bit more complicated, is this idea of transformations we've talked about with rectangular. And so we could say that, say, r is equal to a times f of b minus theta minus phi plus k. Now, a is going to stretch things more from the pole. B is going to have to do with your period, so you'll have more loops in a single rotation, so that leads to petals. Phi is, instead of like an h like we used to have for left-right movement, phi is an initial rotation around the pole, and k you can think of as a superposition, which can lead to limicons. So another way to think about this is your petal number, specifically for rose curves, is based on this y is equal to a sine bx as it wraps around the pole, and you just get overlaps when b is odd. So now a few sample problems. This is looking at symmetry. So the actual problem, 720, number 12, test for symmetry with respect to theta equals pi over 2, so that's sort of like your y-axis, polar axis, which is like your x-axis, and the pole, which is like your origin. For number 12, r equals 12 cosine 3 theta. And so we plug in negative r for r and negative theta for theta, and cosine being a even function, I can take out the negative here. Now this is not the same as my original, so there's not symmetry that way. If I just make theta negative, and I leave r, cosine being even, I end up with what I started with. So that does work, and so therefore we have polar axis symmetry. If I just plug in a negative r for r and leave theta alone, clearly they're different, and so that does not give me a symmetry in that respect. And so this is actually a 3-petal rose, and it's symmetric about the polar axis. So it's got a petal going straight out to the right, and then 2 going off at 120 and 240. So you got 1 going 0, and then the 120 and the 240. Now in this case, we're looking for the maximum r value. So of course 6 is going to remain 6, and we want to do 12 times whatever is going to give us the maximum. Well, the maximum is going to be, we know the cosine is between negative 1 and 1, so to get the maximum value, we want cosine to be 1. So 6 plus 12 times 1 will be 18. So that's our maximum r value for this particular curve. Now as far as finding places where we're at the pole, if we want to find out where we're at the pole, we would set r equal to 0 and solve this equation. And so that gives us cosine theta is negative 1/2. And so two angles that where we're at the pole will be 2 pi over 3 and 4 pi over 3. And of course, if you add multiples of 2 pi to either one, you'll still be at the pole. This is an example of doing a graph by hand. R equals 3 minus 4 cosine theta. What I've done is picked off some individual points and solve for r, and then I plot my my r comma theta values to get some of these points in blue. And you end up getting some repeats as you go past pi. And so I've just filled in with the green here. This should actually go through the pole as well. So this is a limicon with an inner loop. And then this is r equals 5 cosine 3 theta. So this is similar to the one I showed you a moment ago as far as the symmetry with the polar axis, but not with the pole and not with the line theta equals pi over 2. And basically what I've done is I've just put a petal at a distance of 5 here, I've gone out to 2 pi over 3 and put another petal at 5, and then out to 4 pi over 3, another petal over there, distance of 5, and kind of a rough sketch, but that's the idea of how it's going to look.